In this problem, we're using the Biot-Savart law to compute the magnetic field at the center of a circular loop of wire with radius r and carrying a current of I. Then we want to generalize to a flat coil with n turns in it. In other words, n turns of wire with radius r all bundled together with a current of I running through it. So in our diagram, I've already highlighted a small length increment that we call dl vector. This has a magnitude of dl, in other words, a small increment of length, and a direction in the direction of current. So now we start setting up the Biot-Savart calculation in differential form. So there's the Biot-Savart law in differential form. If you're used to seeing this in integral form, you just slap an integral sign on there, and that's your classic Biot-Savart law. So we have that dB vector, in other words, a small vector contribution to the total magnetic field, is given by mu naught over 4 pi times I times this cross product, dl crossed into r hat, then divided by r squared. And I'll post a link at the top to my video on the derivation of the Biot-Savart law. So to use this thing, we need to know what r is. And that little r is a magnitude of a position vector. And that position vector points from the location of our current increment to the observation point for the problem. So there's our vector pointing from our highlighted dl to the center of the ring. And notice there that the magnitude of our vector is big R. In other words, it's equal to the radius of the ring. Next, we need to get a unit vector r hat into the picture. And that's a vector pointing in the same direction as the position vector, but having a length of exactly 1. So now we have to think about crossing dl vector into r hat. And to get this done, we use a right hand rule. We need to orient our right hand so our fingers point in the direction of dl, and we can sweep our fingers through an angle less than 180 degrees to the direction of r hat. Now to do this, our thumb is forced to be oriented out of the page, so that's the direction of the magnetic field contribution at the observation point. So there's our little dB vector. It's pointing out of the page, and we take care of that by writing a dot with a circle around it. So notice, no matter where dl is on the ring, we can repeat this procedure and we keep getting dB contributions pointing out of the page. That means when we add up all the dBs, in other words, when we integrate over dB, we're really vector adding a bunch of tiny dB vectors pointing out of the page. And that means the magnitudes of the vectors simply add together, because when vectors point in the same direction, you just can add their magnitudes. So we can drop the vector hat here and just compute the magnitude of dB. So the magnitude of our magnetic field increment is going to be mu naught I over 4 pi. And then I need the magnitude of dl crossed into r hat. Now remember, the magnitude of a cross product is given by the magnitudes of the two participant vectors. So dl, so the length of dl there, and the length of r hat, but r hat's a unit vector, so that's just 1. And then I need to put in the sign of the angle between the two vectors. Well, dl is at right angles to r hat, so I end up with the sign of 90 degrees there, which then reduces to 1. Now in my denominator, the magnitude of my position vector squared, that's just big R squared, the square of the radius of the ring. So our dB cleans up really quickly here. I end up with just a mu naught I over 4 pi r squared, and then a dl. And so all that stuff out in front is just constants, and now I'm ready to integrate with respect to L. So I get B is the sum of all the little dBs. This is what an integral does. It's just a continuous summation over a bunch of infinitesimal contributions, and I can sub in my expression for dB, and I'm going to move the constants outside the integral. So I end up with mu naught I over 4 pi big R squared, and then I just have the integral of dl along this path where we complete the entire ring. So to complete the entire ring, I just have to go around it once. So I'm going to integrate from 0 to my finishing value of L, which is 2 pi r, 1 circumference of the ring. And when I integrate dl, I just get L, and I evaluate across the limits of integration, and I just get 2 pi r. So our magnetic field is mu naught I over 4 pi big R squared times 2 pi big R. We can cancel one of the big R's. We can cancel a 2 pi. That leaves us with a 2 in the denominator. And we obtain our result for the magnetic field at the center of a ring of current. It turns out to be mu naught I over 2R. Now we just have to generalize to the case where we have n turns in a tight coil of radius big R. And of course, every turn is just going to contribute another mu naught I over 2R. So all we have to do is multiply by n. So we get a slight modification of the formula. The magnetic field at the center of a flat coil with big N turns in it is just mu naught big N I over 2 times the radius. In the next video, we're going to use the Biot-Savart law to compute the magnetic field at a given distance from a finite wire with a current running in it. And this calculation gets really fun because we get to use a trigonometric substitution. I'll post a link to that video at the upper left when it's done, and I'll see you there.